Welcome to the course Business Analytics and Data Mining Modeling using R Part 2. So, in previous few lectures we have been discussing regression based forecasting methods. In particular, in the last part of previous lecture, we were able to model trend and seasonality, both the components. We also looked at the residual plots and saw that the final model that we built was able to adequately capture most of these components. So, let us move to our next important aspect of regression based forecasting. So, there are certain issues when we use ordinary regression models in time series context. So, let us discuss some of these issues and how we can overcome them. So, one important thing is that observations are assumed to be independent. So, whenever we are applying a ordinary regression model, this is one of the underlying assumption in all the multiple linear regression models, that observation, the cases are assumed to be independent. However, if we really look at the time series context, this assumption is typically not valid. So, this assumption is typically valid for the cross sectional data, where we are gathering information on different different rows along different observation rows. So, which is on each unique subject. It could be individual, firm, or anything else. So, those could be different. So, all those instances of that subject, those individuals are going to be different. So, this particular assumption is valid there. However, when we talk about in the time series context, since we are measuring the same instance of the subject, it could be a particular, for example, in this the examples that we have been following here, the riders shape. So, the that riders, number of riders in a month, that is something that we are measuring, and at different sequentially equally spaced points in time. So, we can see this these observation, one observation at time t and the other observation at t minus 1 or t plus 1 cannot be clearly called as independent. So, they depend on previous observation, in the sense that either the for example, if we talk about the ridership, the number of riders will go down or up in some sense. So, the historical values, previous values, and the future values, so they are dependent on each other. So, this is the point, precisely the point that has been mentioned in this slide as well. So, you can see here third point. However, for time series data, neighboring observations tend to be correlated, which is also referred as autocorrelation. So, this is the particular aspect of time series that we are going to discuss now in this particular lecture. So, neighboring observations, they tend to be correlated. So, ridership in the coming month, number of riders that are going to be there in the campus in the coming month, might also be in a way determined by the number of riders which are right now in the current month. So, this dependency is very clear and straightforward. So, this has to be accounted in our time series forecasting. So, as we talked about issues with ordinary regression models, so this particular aspect is not accounted for. So, as you can see in the last point in the slide, this information can be used to improve the forecasting models. Now, we came across this term autocorrelations, which is about neighboring dependence of neighboring values in a time series context specifically. So, let us understand what is autocorrelation in a bit more detail. So, correlation between values of a time series in neighboring periods. So, in a time series data, the neighboring values tend to be correlated, and this correlation is actually referred as autocorrelations. So, this in a sense autocorrelation, the way the name is being used, this in a sense describes the relationship of series with itself. how the series, how the values, when we say the values of a time series in the neighboring periods, they are correlated. So, in a sense a particular series is correlating with itself. So, that is why this particular term autocorrelation is used to explain this kind of behavior or characteristic of a time series. Now, how do we before we can actually account for this autocorrelation in our forecasting model, we need to understand how we need to find out a mechanism where we can compute autocorrelation. So, because autocorrelation is also a form of correlation itself. So, essentially we would be computing correlation between the series and a lagged version of the series itself. So, this is how we are going to compute. So, you can see the second second point and then the first sub point, computing autocorrelation, and correlation between the series and a lagged version of it is going to be used for this. Now, what do we mean by a lagged version of the series? So, a lagged series with lag 1, if the series is being lagged by just one unit in time. So, that would be called series with the lag 1. So, let us see how it is defined here. So, a lagged series with lag 1, values of original series moved forward by one time period to occupy one step ahead time point in future. So, if this is done, what we will get is a lagged series with lag 1. So, original series moved forward by one time period to occupy one step ahead point in future. That means, the value that is there at time t, if you move the series one time period forward, then that values would be corresponding to t plus 1, and the value corresponding to t minus 1 will now start corresponding for time t. So, therefore, the series will create a lag kind of effect. So, this is what we call a lagged series with lag 1. So, another way to understand the same thing is, in effect, time index of original series moved back by one time period. So, in another way we can understand that a particular series, the number of riders in different months. So, if let us say the when there are particular number of riders in the month of March, let us say 2000, and if instead of and before that let us say we had the month of February also, and then January, and then the previous year. So, if the ridership data is in that fashion, and if we want to in effect if we want to move back the time index, then this particular the data that is there for the March, now if we move back the time index, then it would be corresponding to April, right. So, the the March data would now be the February's ridership data would now be used for the March. So, in that sense a lagged effect would be created. Now, when we say computing autocorrelation, so once this lagged series is created, so we compute the correlation of the original series with this lagged series, and that value is taken as the autocorrelation. Similarly, a lagged series with lag 2, so values of original series moved forward by 2 time points to occupy 2 step ahead time point in future. So, once you move the series, once you push the original series in forward 2 time points 2 time periods forward in the time. So, they would be corresponding to t plus 2 and t plus 1, and now the values that you had at t minus 2, that would be corresponding to the current time t. So, in that sense the current time t, the value corresponding value is going to be the value that you had at time t minus 2 in the original series. So, in that sense lagged effect would be created. The same thing we can understand from the time index. If we move the time index of the original series, also we can get the same effect. Now, lag 1 autocorrelation. So, if we have to define what is lag 1 autocorrelation, so it typically measures the linear relationship between values in consecutive time periods. And so essentially if we look at in terms of how we are going to measure it, correlation between original series and lag 1 series. So, we have now understood how we can get the lag 1 series from the original series. Now, the lag 1 autocorrelation is going to be nothing but the correlation between original series and lag 1 series. And if we want to understand what it means theoretically, it is this value is going to measure the linear relationship between values in consecutive time periods. So, how the values in consecutive time periods are linearly dependent on each other. So, that relationship is going to be described by this lag 1 autocorrelation. So, what we are going to do is we will open our studio and do a few exercises to understand what we have discussed so far in a bit more detail. So, let us open our studio. So, the same data set is going to be used. So, before this let us load this library x+x. Now, let us import the data set. So, you can see the data set 159 observations, 2 variables. So, we are already familiar with this data set. So, let us remove any columns if there are any. Let us again have a look at the structure of this particular data set. You can see first column month here and the second column is the number of riders. Let us create a time series object from this. So, you can see in the environment section TSV time series, this has been created. Now, what we are going to do is we are going to compute autocorrelations at various at different lags. So, we will take 1 to 12. So, we will compute autocorrelation between original series and lag 1 series and lag 2, original series, lag 2 series, original series, lag 3 series, original series, lag 4 series and so on up to lag 12. So, we are going to compute these many autocorrelations. Default confidence interval for these computations is going to be 95%, which is typically the default and the function that we are going to use. So, the function in R that we are going to use to compute this is ACF. If you are interested in finding more detail about this function, you can go into the help section and then we can we will just type ACF. And you would see some more detail about this particular function. You can see here the function ACF computes estimates of the autocovariance or autocorrelation function. More detail on the different arguments that are part of this function you can find out from here, right. So, we are going to use this function. In the first argument you can see we are passing this time series object that we have just created, and lag dot max is 12. So, you can see here lag dot max is 12 is the indicating the number maximum number of lags for which we want to compute the at which we want to compute these autocorrelations, right. And then this title for the plot. So, as part of this function we will also get a plot. So, that is also going to be created. So, let us run this. We are going to store all this information, the result of ACF function in this, because few values that are going to be returned from this particular function we might be using it later on. So, you can see if you scroll down the help section you would be able to see the values that are going to be written from this function. So, let us run this. So, you can see a plot for riders has been created. Now, let us analyze this plot. So, you can see these blue blue dots, these are the boundaries upper based on the UCI and LCI, based on the upper confidence level, the upper line and the lower line based on the confidence level that we are going to use. So, because some of these we can see these bars single vertical lines that we can see here. So, they are representing the this line corresponding to the value on x axis of 0. This is corresponding to the original series. Then we have the next vertical line that we have, this is corresponding to lag 1 series, then the similarly lag 2, lag 3 and so on. So, in this fashion we can see a number of lags and autocorrelation between the original series and these lagged series have been computed. So, if we look at the this output, most of these lags is starting from lag 1 to lag 2 and lag 3. We can see most of them are going outside these specified boundary lines based on the confidence interval. So, this in a way is indicating high autocorrelation between original series and these lagged series. So, if we look at the correlation between original series and lag 1 series. So, this particular this particular vertical line and its corresponding value is indicating the level of autocorrelation. So, it is near about 0.6 less than 0.6. So, it seems to be highly correlated. Similarly, for other lags also we can see most of these lines they are on the higher side. So, therefore, the lagged series are highly correlated with the actual or original series, and therefore, it becomes important for our forecasting models to incorporate this information, because this is going to be significantly improving the performance of our forecasting models. So, let us look at these values numerically. So, we are going to create this data frame to have a look at these numbers. So, you can see here for different lags. So, lag 0. So, which is the original series, the autocorrelation of the original series with the original series itself. So, that is of course going to be 1. So, that we can see. Then for lag 1 it is 0.56, and then for lag 2 it is about 0.36. So, in this fashion we can see most of these lagged series are highly correlated with the original series. If we look at the lag 12 series, so this comes out to be 0.75. So, the lagged lag 12 series, this seems to be seems to have highest autocorrelation with the original series. So, there seems to be an annual seasonality here, because the corresponding lag 12 series is having high correlation. Because it is going to be, it is monthly data. So, therefore, those ridership in different months of the year, they seem to be corresponding, they seem to be correlated with each other. So, let us move further. So, here then what we are later on in this code is doing is we are looking at the residual series. So, we will come back to this later. So, let us go back to our discussion in the slides. So, let us understand a few more aspects related to autocorrelation behaviors. So, one of these things is directions of autocorrelation behaviors. So, as we have seen in the output itself, that the autocorrelation value, just like the correlation values, they could be positive or negative. So, in a sense they indicate the direction of this correlation behavior. So, here in this case also positive autocorrelation, it means high values are followed by high values. Low values are followed by low values. So, whenever we get a number and if it is in the positive side, whether this is applicable for correlation values also and autocorrelation values also. So, high values, if the value is positive, this autocorrelation value is positive, then that means high values are followed by high values and low values are followed by low values. So, if we get the negative autocorrelation value, so that indicates that high values are typically followed by low values and low values are typically followed by high values. So, this direction of autocorrelation behavior is important for us to understand, because this is something that is going to help us in terms of identifying different time series component and later on incorporating them in our forecasting model. So, let us move further. So, which kind of autocorrelation behaviors should be explored? So, one thing is we looked at the ACF plot that in the RStudio, and we need to analyze that ACF plot to understand the behavior of time series. Then it is important for us to understand the kind of behavior that we should identify and locate, and the kind of behaviors that we can easily incorporate in our forecasting models. So let's discuss some of these behaviors which can be explored. So first one that we are going to discuss is stickiness. So what we mean by stickiness? So it essentially means that a strong and positive lag 1 autocorrelation, if that is there in the ACF plots as we saw in the RStudio, if there is a strong and positive lag 1 autocorrelation, then this particular thing indicates this kind of behavior, stickiness. The strong and positive lag 1 autocorrelation indicates the stickiness in the time series. So what it means is consecutive values move in the same direction. So as we saw in the ACF plot, lag 1A had high autocorrelation value about 0.56. So that indicates that there is some stickiness in the time series that we are analyzing. So the higher values, the consecutive values, they tend to move in the same direction. Let's look at the another autocorrelation behavior, which is swings. So when do we observe these swings kind of behavior in the time series? When a strong and negative lag 1 autocorrelation is present, then probably that is going to indicate swings in the series. So what does this mean? Alternate values move in the opposite directions. So therefore first the higher value is going to be there, then it is typically going to be followed by low low value, then it is going to be typically followed by high value, and then again. So high low. So those kind of swings that we see in a particular time series, that is the kind of behavior, that is the kind of characteristic that is going to be shown if there is a strong and negative lag 1 autocorrelation. So in the data set that we are using, the time series that we are analyzing, so we had positive lag 1 autocorrelation. So probably stickiness is the thing that is the behavior that is being exhibited by this riders data set, and not this kind of behavior swing. Third one is the cyclical pattern. So when this kind of behavior is indicated, so strong positive or negative autocorrelation at lag CL, where CL is the cycle length. So if we expect that a kind of cycle in the time series, and we see a strong positive or negative autocorrelation at that particular lag, the lag which is indicating the cycle in the series. So that would in a way indicate towards the cyclical pattern that is there. So for example, this behavior at lag 12 would mean annual seasonality. So we looked at the when we saw the ACF plot, we saw that the highest autocorrelation value that was there, it was at lag 12. So it means then that probably there is a cyclical pattern. So this because it is the lag 12, so this is the annual seasonality that seem to be present in the rider data that we have. So as we have been discussing that the regression based forecasting methods that we have been using till now in few lectures. So we were able to model the trend and seasonality, and then we had the residual series. So in that residual series that we had in the previous lecture, we can check autocorrelation in that residual series, and we can examine if there are any patterns, autocorrelation specific behaviors that are there, and then we can model that also in our regression based models. So to examine the adequate modeling of different patterns, we can check the residual series. If some pattern has not been modeled, then it would be reflected in the residual series, as we have been doing in previous lectures also. For example, seasonal pattern. So, there is going to be no autocorrelation at seasons lag. So, if we are able to adequately model the seasonality component in the time series, then autocorrelation should not be visible in the ACF plot at the seasons lag, right. So, this is one. So, using autocorrelation to improve forecasting models. So, one thing that can be done is we can directly account for autocorrelation into the regression model itself. So, such models are called autoregressive models. So, for example, if we know that our original series is going to be depending highly depending on the previous points ridership. So, if at time t the riders number of riders are there and this number is highly dependent on the number of riders that we had in the previous month. So, this particular aspect can be included in the regression model itself, and when this kind of thing is done, we call these models as autoregressive models. So, this is one approach to incorporate autocorrelation and improve the forecasting performance. Then the second approach is multi-level forecasting. So, in this case what we do is first we apply our regression based models, and the residual series is then again used to build a second level forecasting model. So, different levels are used to adequately capture different aspects of time series. So, autocorrelation could be captured in the some second level of the modeling. So, now let us discuss a bit about autoregressive models or AR models. So, these are linear regression models where predictors are the past values of the same series, right. So, as we understood that the values at time t, if they are dependent on the values at time t minus 1 and other lagged points, then this can also be said that predictors are the past values of the same series. Linear regression model with original series as output variable and lagged series as predictor or the autoregressive model. So, the linear regression model typically typical standard multiple linear regression equation is y and y equal to alpha beta 0 x 1 beta 0 plus beta 1 x 1 plus beta 2 x 2 plus beta 3 x 3. Now, in this instead of x 1 we can have y t minus 1. So, what y t minus 1 is indicating is the lagged series, and that lagged series is being used as a predictor in the in a way in terms of predicting the values at time t. So, y t is going to be beta 0 the constant term plus beta 1 y t minus 1 plus beta 2 x 2 plus beta 3 x 3 and so on. So, in that sense the lagged series can also be used as a predictor in the regression model itself. Now, more general class of such models is called autoregressive integrated moving average or ARIMA models. So, these AR models they are extended and the moving average aspect was that is also integrated, then we reach to the more general class which is called ARIMA models. Now, let us look at the one example. Let us look at one example. So, for example, AR2 we are looking for autoregressive model of order 2, then how the regression equation can be written as you can see here y t beta 0 plus beta 1 y t minus 1 plus beta 2 y t minus 2. So, you can see this autoregressive model is of order 2. So, that essentially means we have two autoregressive terms here in the regression equation. So, one is y t minus 1 and then another one is y t minus 2, and that is why the order of this autoregressive model is indicated as 2. So, then the next important aspect of the autoregressive models is estimation. So, estimation of the regression model with AR terms. So, one approach is the that ARIMA estimation techniques that could be used, and there are certain reasons for it to be preferred over ordinary linear regression estimation. or OLS estimation. The reason is also something that we have discussed before, because of its ability to account for the dependency between observations. So, if we are going to use OLS regression, the estimates that we are going to be computing, they would actually be also based on the assumption that observations or cases they are independent. But if we use the ARIMA estimation method, they account for this dependency, and therefore the estimates can be more accurate. Now, in the AR modeling, if we look at from the modeling perspective, how do we determine the order of the model, because a series could have high correlation with a number of lagged series of itself. So, therefore, how do we determine the order of the series, where do we stop, or what order do we finalize. So, choosing the order of the model is a tough task. Especially in the context when original series contains trend and seasonality patterns. So, when both these patterns are present, then it becomes even more complex. So, what can be done is several initial data transformation can be performed, and these data transformation would essentially indicate us in a sense the order of the model that could be used. So, another approach of AR modeling could be that instead of AR models, we can also use the more general ARIMA models. So, why just stop at AR level, why not use ARIMA models. So, however, these ARIMA models they have their own pros and cons. So, few important aspect about these ARIMA models is that they require higher level of statistical expertise, the kind of data transformation, the kind of statistical expertise that would be required, that would be more engaging, and also they are considered less robust. So, every time probably you apply an ARIMA model and you do certain changes in your modeling, then the results might vary. So, the robustness is that is under question. That is why ARIMA models are not that popular in the forecasting in the forecasting arena. Now, let us discuss the another aspect, use of multi-level forecasting, something that we discussed also. So, the main idea is to incorporate autocorrelation. So, this particular approach is, instead of using ARIMA, which is less robust and requires more statistical expertise, we can use multi-level forecasting, where to incorporate autocorrelation, simple straightforward approach. So, what we need to do is it will require us to build a second level forecasting model for the residual series. So, we will have a first level forecasting model, which would be capturing the different components of the time series, trend, seasonality, and the residual series of that model. Then we can look for the incorporating autocorrelation. So, we can develop a second level forecasting model. So, short term forecasting performance might improve due to utilization of autocorrelation. Why we call it short term? Because we say that autocorrelation essentially means that neighboring values are dependent on each other. So, therefore, short term forecasting would actually be influenced by this dependence, and therefore, short term forecasting performance, if we incorporate autocorrelation, then this short term performance can be improved. So, the second level forecasting model is essentially going to help us in improving this short term performance, because the long term performance might be determined by trend component and the seasonality component, which we should have already adequately modeled in the first level forecasting. So, second level we can focus on, we can incorporate autocorrelation and improve the short term forecasting. So, what are the steps? So, we use first level method, multiple linear regression, to forecast future values of the original series. Main idea is to capture trend and seasonality patterns. So, example, something that we have done in previous lectures, quadratic trend and seasonality modeling for bicycle ridership data set that we have done. So, this is one that we do in first level method. Then in the second level method that we are specifically discussing in this lecture, the AR model can be used to forecast residual series. and need for initial data transformation is not required, since residual series is not expected to have any trend or seasonality patterns. So, these trend and seasonality patterns we should have been able to adequately capture in the first level, and the second level therefore, only the AR components would be remaining and we would be modeling them in the second level method. If we talk about the ARIMA, these transformation data transformation would be required, because everything is typically done in the same go, in the same in one model itself. So, combine the results to produce the final forecast. So, final forecast is going to be first level forecast plus second level forecast. Now, fitting AR model to the residual series. So, first we can examine the autocorrelations of the residual series. We can then select the order of the AR model based on the lags where autocorrelation appears. AR1 model for the residual series, if we are denoting RT is the residual series, then we can write in this fashion. So, for the residual series RT beta 0 plus beta 1 RT minus 1. So, in this fashion we can write the AR1 model. Similarly, other models can also be written in the similar fashion. So, what we are going to do is we will open RStudio and then we will do an exercise to understand a bit more about the auto regression. So, let us see here that we will just quickly run through this part, because we have done this in previous lecture. Let us compute season, this length, because we would be computing t square, and then let us compute this data frame. Let us look at the first 6 values. You can see riders t square and season. So, this quadratic model we had done in previous lecture also. Let us do the trimming. So, df train and df test. Now, we are going to just build this linear regression model using LM function. So, this will give us this residuals. So, using these residuals values we can create our residual time series. So, let us do this. Now, we are interested in understanding this particular residual time series. So, again you can see we are using ACF function here to look at the autocorrelation. We have the lag max 12. So, let us compute this. So, you can see here in the plot section that we can see high autocorrelation values for lag 1, 2, 3 onwards. If you are interested in the actual numerical values, we can see from here as well that 0.65, 0.52. So, we can see in this fashion. Now, you would see at lag 12 the value autocorrelation is within the bounds here, and also the numerical value is also on the lower side. So, there we can see that seasonality and those aspects have been adequately captured. It is just the autocorrelation component that seems to be there. So, what we can do is we can build an AR1 model on this residual series. So, for this we can use AR function which is available. So, in this AR function more details you can find out in the help section. You can see we are passing on this residual time series. Order max is 1 because we are building an AR1 model. Why we are building AR1 model is because we feel that once you capture AR1 this relationship will propagate itself, and the other orders we do not need to explicitly include in the equation, because once we do AR1 this relationship is going to propagate, and more often than not this typically gives us a good enough model. So, let us run this and let us look at the coefficient here. You can see 0.6521. Now, the same AR1 model we can also build using the ARIMA function. So, this is also available. So, what we need to do there is we need to specify the order. So, since we are just focusing on the AR model, so just that order is specified and the others are initialized as 0. So, we can use this function. More detail on this ARIMA function as well you can find from the help section. Again, if we look at the results, now if you look at the coefficient value, this comes out to be 0.6496. If you go back and the coefficient value that we had using the OLS, it was 0.6521. So, there is slight difference. slight adjustment in the ARIMA estimation method in comparison to OLS. So, OLS, because it is assuming the observations are independent. So, 0.6521 is there, the coefficient is there for AR1 model, but if we look at the ARIMA estimation, this value decreases a bit, it becomes 0.6496. So, that is the difference in the estimation, because the ARIMA estimation is accounting for the dependence between observations as well. Now, we can have a look at the forecast for the we will look at the April 2016 this values till March 2016 we have used for the training. So, we can look at the actual value that was there 4069 DF text. So, we can have a look at this value. So, this is the value. So, now if we apply, if we use the predict function to use this model and make a forecast for the 148th value, that is part of the test partition, the first value of test partition. So, this is the actual value and we are trying to predict this. So, let us run this code and let us have a look at the value. So, this is the value, this is the forecast for the residual. So, this again can be used. So, this is the second level forecast that we have now just done for the residual using AR1 model, right. Now, if we look at the first level forecast for the original by the regression model, so that can also be done. So, mod this we have already model we have already built, can use this. So, this was the first level forecast 4118 and the second level forecast is -22. So, we can do a summation of these two forecasts and we will get the our two stage model. So, first one regression, the second one AR1. So, you can see final 148 is the first level forecast FL148 and then the correction. So, we will get this value. So, you can see 4095. So, if we compare this with the actual value is here. You can see actual value is 4101. So, after the second level forecast, the final value that we get, this value is much closer to this actual value in comparison to the first level forecast that we had, right. So, the second level forecast, the autocorrelation when we incorporated autocorrelation that is present in the series, our forecasting performance actually improved. So, that is very clearly visible in these values as well. Now, we can plot these the residual series and forecasted residual series to see how adequately it is being modeled in overall sense. So, let us plot. You can see this is the plot for the residuals. Now, what we are going to do is we are going to add the forecasted residual series. You can see the plot. So, the red line, this is quite closely following this particular plot. So, we can see that that is why this is adequately being modeled, the AR component is adequately being modeled. We can look at the ACF value also to again reconfirm the same thing. So, we can call ACF function on this and we can see now here in the ACF plot, as you can see, we zoom in, no lagged autocorrelation values at different lag is beyond the bound, that blue line that we see. So, therefore, the autocorrelation has been adequately modeled here. So, if you are interested in the numerical values, you can see here most of the values they are quite low. So, we can see here. So, let us go back to our discussion. Now, another important aspect of regression based forecasting method is evaluating predictability of a time series. So, what do we mean by this? So essentially what we mean is whether applying forecasting methods on a particular time series would yield any meaningful forecasting model. So, for any time, this is especially true for a time series, that before we attempt to build a forecasting model for a particular time series, we need to make sure whether that series has some forecasting value for us or not. So how do we find out? Otherwise different models and different things that we might try out, they might not work well or might not provide us a meaningful forecasting performance. So how do we understand whether a time series should be forecasted at all? So that is something that we are going to discuss. So how predictability of a time series can be determined? So this can be tested by examining whether the series is a random walk, right. So how do we do this? So let's first understand what is a random walk. So random walk is a series where values change from one period to next in a random fashion. So for example, predicting stock prices. So typically it is understood that from the efficient market hypothesis that these asset prices they are they are randomly because it is very difficult to determine how they are computed, how they are determined. So predicting stock prices is kind of a random walk, and no information is going to help us in terms of building a model and having a meaningful forecast. So if we are able to test for a series whether the values change from one period to next in a random random fashion, then we would have a sense whether there is any purpose in terms of predicting a time series. So how do we define random walk model? So this is a special case of an AR1 model where beta 1 is 1. So the equation can be written in this fashion: yt beta 0 plus yt minus 1 plus epsilon. So you can see the coefficient, the beta 1 is 1 here. So that means yt is dependent on the previous value, that is yt minus 1, and then the noise term. So that means if anything is part of noise. So and if this the value is mainly dependent on yt minus 1 and the remaining part is noise, which is something that we cannot further use for improving the forecast. So if this is the case, then probably the series is a random walk. Now how do we test? So we can rewrite this whole thing as: to test whether a series is a random walk, AR1 model is fitted. So that is first one. So essentially we are checking for this hypothesis, this alternate hypothesis, whether beta 1 is equal to 1 or not. So beta 1 not equal to 1. If beta 1 is equal to 1, then null hypothesis, it is null hypothesis, it is going to be accepted. That means the series is a random walk. If it is not accepted, then probably there is some scope, some forecasting of that series can be done. So what we are going to do is we will go back to our studio and do an exercise to find out whether a particular series is a random walk or not. So for this we will look at the S&P BSE 500 monthly closing prices, and we will look at analyze whether this particular series is a random walk, whether it makes sense for us to build a forecasting model for this series. So let us import this data set. So this is the this is the structure of the series. So we are going to create a time series vector here. So you can see these are the values that we have. So we have 132 values from 2007 to 2018, and what we are going to do is here now we will call this ARIMA function, and we will pass this time series vector that we have just created for this time series. And you can see in the order you can clearly see we are just fitting the AR1 model, and once we do this we will get the coefficient, and this is the coefficient that we get. And now you can see the value of this coefficient is 0.9931. The value of the coefficient is 0.9931. This is very close to 1. So essentially if we go back to what we were discussing, this beta 1 that we have fitted the AR1 model, and the beta 1 value is close to 1. So that means this BSE S&P BSE 500 time series monthly closing prices, this seems to be a random walk. Therefore, forecasting this series using any model might not be meaningful, right. So, with this we would like to stop here, and in the next lecture we will start our discussion on smoothing methods. Thank you.